Okay, our goal today is to construct a two-sample t-interval. And what this is going to do is give us an estimate, a little window, a range of values that gives us an idea of where we can be fairly confident the true difference in two population parameters lies. So let's start with just some basics. Let's say we have two populations. Maybe they're normal, maybe they're skewed, maybe they're funny shaped. We have no idea. Let's call this population 1, and let's call this population 2. As long as our samples are big enough, it doesn't matter what shape the population is. That's the central limit theorem. But our sampling distributions for each population, sampling distributions of x bar, will be centered at the true population mean, and they will have a spread based on the sample size. This is going to be the population 1 sampling distribution, and this one's going to be population 2 sampling distribution, x bar 1 and x bar 2. We've talked about things like this before, but now what we're interested in is combining the two and saying, what if we chose a bunch of people from population 1 and a bunch of people from population 2, and we created a new normal curve that's measured as x1 minus x2, x bar 1 minus 2. And it could be 2 minus 1. That's not the issue right now. But what we want to do is combine these two into a new curve and talk about how confident are we that this true difference is the number that we get. Okay, population 1 has a true mean. Population 2 has a true mean. That's the one that nobody knows. We can only estimate. Our new distribution should be centered at the true mean if it's unbiased. And so we can go on from here like we have in the past. There are some differences, mainly in the formula. We know that this curve will have a normal shape. We know that its center will be at the true center, but its spread is the biggest difference. So we'll just cut to the chase and show you the formula. The spread of this, the standard error of this new curve that we're dealing with, is here. All right, it's the square root of sample standard deviation 1 squared over the sample size of 1, and then the same thing for population 2. We still have a t-star critical value, and notice our statistic is the difference in the two samples that we choose. All right, so you can see the similarities with some obvious key differences, but if you know the formula, there's a lot of plug and chug to it. Our conditions are going to also be fairly close. And we can always feel safe that our calculator can do all this math for us in the on the exam and when we need it to. But we're going to do this one the old-fashioned way. So let's talk about the conditions. We are choosing from two populations. Both of those selections need to be random samples. That's always the case. That's going to take care of a lot of the issues that might come up. We need each sample to be big enough. Either the populations were normal or the samples were greater than 30 for the central limit theorem to apply, greater than or equal to 30. And the difference here between a t interval and a two-sample t interval is we have another kind of independence. We need for the individuals in each sample to be independent, okay? And we also need the two samples to be independent of one another. And like I said, all of this is taken care of by taking simple random samples that are not more than 10% of the population. Something weird would have to be going on in order for the samples to somehow be related to each other, or the individuals to be related to each other. Okay, so we're going to use AP students as an example. I'm going to choose 127 from Kentucky AP Stat students, get their average exam score and standard deviation, and I'm going to choose 154 from Ohio and get their average and standard deviation, and construct a 95% confidence interval for the true mean difference in scores. Okay, there is, if you were all knowing and you knew the actual average from everybody in Kentucky who's ever taken the test and from Ohio, you could subtract those numbers and you would know who does better in overall. We are estimating that. That's what a confidence interval does. It estimates an unknown value. So let's just take the necessary info and plug it into place. Okay, we're plugging into this formula. So my statistic, I'm going to set this up as Kentucky minus Ohio. There's no right or wrong for that one. My Kentucky score was higher, so that's going to make it my statistic positive, but it would be fine either way. So my statistic is 3.4 minus 3.25, or 0.15. Okay, plus or minus, next in the formula, T star. Okay, now we've got two sample sizes. The way we're going to deal with this is we are going to use the smaller sample size. So I'm going to use 126 degrees of freedom. And the value from the chart in the back of my book is 1.984. And that's actually the 100 degrees of freedom line, because I'm being conservative in using the smaller sample, the 127, which gives me 126 degrees of freedom, but then I'm actually going up to the line of 100 because that's the next biggest number on my chart. I think it would have been the same if I'd used the 154. At this point in the chart, the values are all so close, it doesn't really matter much which one we use, but we're going to use the smaller sample. Okay, now here's the big difference in our formulas from now and previous. We need the square root of the standard deviation squared over the size for sample 1. So my standard deviation was 0.75 squared over 127 plus the 0.8 standard deviation squared over 154. All right, so this is literally just taking the info from the question and putting it all into place. The sample, I have 6 numbers in the question, and then the T star is the only one that I really had to find. All right. Now, I'm going to do some math. Pause. I encourage you to pause and work this out and get the number on your own, and I'll be right back with that math. Okay, so after typing this in my calculator, and you can type it in one big line as long as you're careful with your order of operations and make sure you get parentheses where you need them and not where you don't need them. According to the formula, I get negative 0.034 to positive 0.334. So let's talk about that, what that means before we write our interpretation sentence. I am 95% confident that the true difference is somewhere between 0.034 negative 0.034, which would be Ohio beat us by 0.03 for us, Kentucky. I'm in Kentucky. Somewhere between that and Kentucky won by 0.334 on average. All right, that's what this 95% confidence interval means. So what you should watch out for is follow-up questions that ask you, is this evidence that Kentucky scores higher? Now, this is a gray area. It's very much centered on the Kentucky side. I am pretty sure that on average, if I knew every score in Kentucky, that would be higher than every score in Ohio. However, according to this interval, which crosses over 0, I do not have evidence at this confidence level of 95% that Kentucky did better. What you kind of have to think of it as is like this. Anything inside this interval is a valid, reasonable assumption or expectation of what could be true. And since 0 is in that, that would mean the two states were identical. Now, when it starts to get pushed to one side, then that might change things up. I'm going to tinker with the 95% a little bit and see if we can see what happens in that case. Okay, so in my calculator, what you'll notice is if you go to stat, over to tests, and then down a little bit, this is a 2-sample T interval. So this will allow us to show the calculator and play around with that 95% a little bit. A 2-sample T intervals, what we calculated. So there's the stats that had the 3.4 average, the 0.75, and so on. You can leave pooled on no It'll ask you, do you want it to be pooled or not? We can talk about that later. But when you calculate, this is going to be pretty much the numbers I got, negative 0.0324 to 0.332. The difference there is how many degrees of freedom they used. All right, the calculator gives you specifically 274.4 and so on degrees of freedom. We used 100. So don't be surprised if your numbers vary slightly from the calculator if you do this by hand. Okay, and forgive me, my calculator just crashed on me, but I went into my other calculator by hand and I tried a couple of different options. And if I played around with that percentage and I made it 0.85 or an 85% confidence interval, then what turned out was 0.016 to 0.284. So what I was saying about this interval crossing over 0, ours does at 95%. So at the 95% level, we cannot be confident that Kentucky scores are higher on average. But if I change that level to 85%, that allows me to narrow my window a little bit to get a narrower confidence interval. And at 85%, I can be confident that Kentucky scores are higher. So look for questions that ask you, are you confident that one is higher than the other? What you have to go by is, does it cross over 0 or not? Ours did, but I just don't want you to hold that as sacred because this question happened to be 95%, and a different level would make it not cross over 0. So the only thing left to do after all that is to interpret. I am 95% confident. This is the wording that you should be familiar with at this point. At the interval negative 0.034 to 0.334 captures the true mean difference in AP Stats exam scores between Kentucky and Ohio students. Okay? So don't skimp on the words. You can abbreviate a little bit, but on the test day, that's when it really counts. So write a good sentence with that interpretation. Okay, so just a quick review. We're doing confidence interval, but it's for the difference between two means. There is an actual difference out there somewhere. We are trying to estimate it using this new version of our confidence interval formula. All right, that's going to do it for this one, Young Out.